And whatever that fast So let's continue for the equivalent circuitry. So last week we mentioned about this equivalent circuitry. So that's one of the most important item for induction motor. So we usually convert all the induction motor to this equivalence circuitry. So from here, you can see that we have the stator circuitry. This we call it the magnetizing circuitry, and this is the rotor circuitry. So from all the proof we did before, we found that the rotor circuitry will be a lot of information here, including we have the turns ratio. We also including the S, the slip in here. Yes?
How does this differ from the transformer circuit or equivalent circuit? Because it looks very similar.
Yes, that's why we need to use this circuitry to show you about the correlation between the transformer circuitry and the induction circuit. You can see that that's the question I also like to ask all of you. What do you think the difference between the two equivalent circuitry? Obviously, you can see that the circuitry is exactly the same. We can also see that we have the stator circuitry here, which is these two items, the same as transformer. These two are the same as in the transformer with the core losses and also magnetizing inductance. But this could be different. That's key important. You see here, you got the A here, this transformer ratio, the same as the transformer, but you got the S here. S is related to slip. Induction motor is a rotating machine. So the motor is rotating. There will be slip. The slip means the frequency lagging behind the synchronous frequency. What's the synchronous frequency? Now it's time to ask you a question to prepare for your exam, right? Synchronous frequency. Yeah. Yes.
I have a question about this.
What's the synchronous frequency first?
The synchronous frequency that is the frequency at the synchronous speed, right? That you see the frequency of the stator rate.
So to be more exactly, I mean the synchronous frequency is the frequency we can able to synchronize with the supply frequency. But the supply frequency is the electrical frequency. The synchronous frequency I mentioned here is the actual mechanical frequency trying to synchronize with the electrical frequency. In this case, they are the same but different by the token. Right? So Adam, what's your question again?
I was going to say this is the equivalent circuit for the motor's actually on, right?
Yes. Then the motor is rotating. That's why you have S here, the motor is now operating with S. S means there must be some certain rotation of the speed there. But S can be from 1, which means standstill, to 0, that means they're synchronous. Same speed, yeah. But usually we don't like to the same speed because later on when you see the motor curve at SU 0, you get low power, low induction. Okay. So they are exactly the same. I like to use this circuitry because you can correlate them with a transformer, but only difference is the S. So that's why the circuit is so beautiful. I should say it's really beautiful because it's just the same, but only different by S. You can relate them into a stationary transformer to a induction motor with a rotating, but with the S. So that's why you give you something you can able to correlate to what you learned in the past. The transformer is standard. We have been using it for a long time and in circuit theory, but now when we go for the induction motor, we can see a lot of similarity. And then we can also use that circuitry to work out all the power equation, torque equation. So you have learned some power equation, which I can go through again. And then in a few minutes, you're also going to learn about the torque equation, which is based on this one to derive the torque equation too. We need the torque equation so that we're able to understand how to control motor. You know, motor rotation, we can control them, control the speed, control the torque, and then in this case, you can make use of this control equation circuitry to understand how to operate on the motor. So that's how we're trying to do. So let's go through a very simple example to show you some basic concept about how to relate power and the slip. And say we have a three-phase motor, 15 horsepower, 460 hertz, and the motor rated speed is 1728 RPM, 4 poles. And then the losses, including vintage and frictional losses, is 750. So we now calculate mechanical loss power, air gap power, and the rotor copper loss. Because we got a number of standard equation, we are able to relate the air gap power, output power, and the rotor resistance loss. So that's why we can quite straightforward, able to calculate all the three items. Firstly, we change them into SI unit. So 15 horsepower and convert to SI unit become 11.9 kW of power. And mechanical power actually summation of a few things. Once the shaft output, the mechanical power connect to output, plus all the friction, vintage loss, everything. So that would be because the vintage is 750. So that's why you're able to add these two together into our total losses. So that's actually losses delivered from the air gap. The air gap, as I mentioned a few times, air gap power, when we go through the air gap, we translate into two power. One will be all the mechanical power, including SB or the mechanical items. Another one will be the rotor couple loss. So mainly about these two. Rotor couple loss is resistive losses. So let's firstly, before we calculate air gap power, so let's go to understand more about the synchronous speed. Synchronous speed, we have standard equation relate to the input frequency F1, which will be our 60 Hertz here, 60 Hertz. I think now you have been using this formula so many times, you're able to write down a formula without thinking, right? So now then we can divide by the pole pair is 4 pole here. Then we are able to get 1,800 RPM. And then the slip mean is now our synchronous speed. Again, the synchronous speed mean is the electrical frequency after we translate the mechanical frequency that divided by the pole pair. So we got this 1,800 RPM minus the rated speed. The motor cannot run at 1,800 RPM, otherwise same speed we have no induction. We need a little bit of the difference. So that's why the rated speed of the motor usually will be less than the synchronous. So we have this one down. And here, then we get the slip at the normal operation. So under that operation, 4% of the slip. Then you can see that the air gap power, we have standard formula here. So do remember the formula? We mentioned quite a few times. So 1 minus S portion is the mechanical power. And then the other portion, so this is mechanical power, that's why we get the air gap power. Very simple, straightforward equation. And the other portion, S portion of the air gap power will therefore give you the copper losses, right? So 2 portions. So that's why to operate on this example is quite straightforward. 1 minus S is mechanical output, S portion will be the rotor losses. That's all, right? Okay, no, good. So next tutorial, try to understand further about it. Do a few tutorials. They're very similar. I just make sure I do a few tutorials, make sure you understand what it is. And then in the next tutorial homework, then you're able to handle them properly. So this tutorial looking into a 3-phase motor, 25 horsepower, 400 volt, 50 Hertz, 1440 RPM. So when they say 1440 is the rated power, rated speed, so that's the normal operation, rated speed you can go up to. And then you try to deliver full power to load, and then the combined vintage friction, all the losses is 900. So now then we are asked to calculate the mechanical power, the synchronous speed, and also the slip, the air gap power, and the rotor couple. It's a similar equation. So we just do a few times, we should able to 100% familiar with how to do that. So again, the horsepower 25, we just convert them by using this ratio, convert into SI unit, kilowatt or watt of power. So mechanical power is, so we have all the losses in here, right? So the shaft power is equal to this one. Then that's why the summation is total possible power through the air gap to the mechanical output. So again, we calculate synchronous. So it's the standard formula. We have 50 Hertz in here. Then we're able to get the RPM, 1,500 RPM. The slip at that point will be because the rated speed is 1440, and then the synchronous speed is 1500. So we got 4% here. So anyway, we found that most of the motor, the rated speed usually just a few percent, usually less than 5. I mean, 2 to 5% is quite common. If you see any motor, 10, 20% is
not quite right. Okay, 1% is not possible, it's too small, right? And then now then air gap power would therefore mechanical power. Okay. I need to change the battery, yeah? And then divide by 1 minus S, yeah? So that's the power. And then again, the rotor power, from 2 mean the rotor, and then it's S multiplied by air gap, also give this. So that's why you can see that 2 examples show you the standard method to correlate the air gap power to rotor resistive loss and also output power to the shaft. Okay, so very 2 examples show you very standard method to do that. I think you all can handle it. So finally, then we just look into the efficiency. So efficiency of motor relate to a few things. Although I think you learned the power and power factor, right? Have you done the power factor? Power factor for 3-phase or for single phase AC, right? You have done that for EE65, Engine 65, not yet. But soon, right? Very soon. You're now still learning the DC circuitry? I'm sorry. So which session are you learning now for the electrical circuit?
We're about to go into hospitals.
Okay. Anyway, but so AC and no matter single phase or 3-phase, the standard equation with the voltage times current times the power factor. So this is our power factor. So that's the standard equation. 3 means 3-phase. So when the V1, when these are the phase parameter. So you can imagine you got 3-phase here. So each one we got the V1, we got current I1. So the power for each one of them will be equal to V times I times this power factor. So we have to multiply by 3 in here. Of course, multiply by 3 in here because we're talking about per phase circuit. So that's why I multiply by 3. Later on, we'll show you some scenario when we are not only per phase, we're using something other combinations. You need to be careful about the root 3 or 3 relationship. So anyway, the stator winding, we have the power losses. Of course, if the 3 of the 3-phase multiplied by I square R1. So that's standard formulation. And then we also the input power. So in here, we say input power, we did not consider the stator losses. We just mean the input power through the air gap. Although there may be power losses in the stator, at the moment we try to make it simple. Just say the input power is equal to air gap power, and then P2 is the power is the losses in the rotor. So that's why the power output is 1 minus S. So in theory, the efficiency for the rotor part is 1 minus S. Because 1 minus S is the portion go to the mechanical output. So there's a maximum possible efficiency for the motor. Of course, when we include the stator losses, like the stator winding losses or her other losses, then the efficiency will be reduced. So that's the maximum efficiency you can get. So if a motor is say 4%, the maximum efficiency will be 96. Cannot be anything higher than 96 in theory. And then must be lower than that because 96 have not considered the stator winding losses. So that's the maximum efficiency. I think we got this equation. We have mentioned this equation by some times, right? Do you remember the equation? Yes? Yeah. Okay. So again, the maximum possible efficiency for induction motor is 1 minus S. Cannot be higher than that. It can only be lower because we did not consider the copper losses in the stator yet in this formulation. So the final part, just go for a few tutorial, make sure you fully understand, memorize it. Just some straightforward tutorial. We got 4-pole machine, 60 Hz induction motor, running at 1740 RPM using the simplified method. Simplified method means we're not going to calculate the state losses. We can if you like to. And then estimate the efficiency without considering the stator losses. Then we need to calculate single speed. Is the standard equation, right? 1800 RPM. And then we have the rate is this one, then we can get the slip of operation. So the efficiency at that particular slip will be equal to this efficiency using 1 minus S formulation. Okay, so that's a standard method. We calculate the efficiency of an induction motor. Very simple, straightforward.
So from now on, you can go to some website to check the specification or some industrial that they provide to you. They usually mention to you their efficiency. They also mention about their RPM. So you can check that number using my tutorial. We examine their efficiency if they are sensible, because that is the maximum efficiency. Again, we can't get higher than that. Right? So that's the information to show you how we understand the specification and the maximum possible efficiency. So next, another example, again, make sure you understand them. So now we have 6-pole machine, 50 Hertz, and then 960 RPM at full load. What is the approximate efficiency using the simplified formulation, right? So again, we got the standard formula, this one, and then we got 1000 RPM. So we got 960 in here, we got 4%. Again, usually just a few percent for the slip operation. So now the efficiency 1 minus 0.04, we got 96%. So after we've done it a few times, you now should be 100% familiar with the basic correlation between the air gap power, rotor losses, efficiency, S, 1 minus S, right? So basically this chapter is telling you this. Although you see we got very complicated equivalent circuitry, we can also derive the torque equation from this circuit. That will be next chapter. For this chapter, what you need to understand is mainly about all the basic formulation, about the air gap power and everything. So similarly, another tutorial will show you if an efficiency of motor is 95%, can we able to get the approximate full power or full load speed? So we can do it in a reverse manner. So if efficiency is this one, then that's why I can get the slip will be 0.05 reversely. So once we know the speed is 0.05, then the synchronous speed is again is 50 Hertz, with therefore 1500, and then we revert the formulation, then we can therefore get 1500, 0.5, then we can get the motor speed. Yeah, so that's 1425. So by using this simple formulation, you can play around with the parameter. You're able to obtain all the parameter in this manner. All right, get that? So now then, for the actual comparison, because just now we're only looking into the perfect condition without stator. So now then, if we look for other parameter, what will happen then? So if a motor is input power 25 kW and the output power 23 kW, the slip is 4%. Compare the efficiency using the simplified formulation. So the efficiency will be 23. So there's a typo mistake. 23 over the 25, so that will be 92.8%. So that is from the parameter of the given data, the efficiency will be 92.8%. And then the efficiency of the perfect condition, 4%, you give you ideal condition, will give you 96. So you can see the difference. So the difference is 3.2%. That difference is due to all the losses we had not considered in the perfect equation, which must be the stator losses, core losses, this item. So you can see the comparison between two efficiency. The manufacturer will give you their efficiency. So that is their efficiency consider everything. So probably you can see here, the ideal line efficiency will be 96. And then, but however, the measured efficiency, including everything, will have core losses, data losses, then will be due further. So that's how you can see the difference between full efficiency. All right. So I think this few example, we've done 4 to 5 examples. Now after this, you should be able to handle that. Okay. You got that? Yes.
The simplified efficiency, it's not taking into account the losses. Like, why is that allowed?
Yeah, that's a pretty good question. The thing is, for motor and master, we have a number of formulations. We should under the ideal condition, how the efficiency or how the slip look like. So the simplified formulation, 96, this one, you only give you the ideal condition. But we happen to the formula is so simple and so simplified. So it help it easier to understand what happened in the efficiency and the sleep in the water side. If the formula come up with really complicated with a lot of the parameter, I won't introduce to you. We just happen to be so straightforward and simple. Why don't you remember this formula and give us some additional information how the water circuitry, like by using this formula, you're able to understand the efficiency performance in the water side after the air gap. Simple formula, 1 month voice, that's all.
So I do have some formulation relate to the efficiency when we consider the stator losses. That would be really complicated. I think I will show you something in the next chapter. But bear in mind that is something you can help you to memorize the performance of motor in a simple manner. Because as an engineer, I always like you to understand something, to memorize something, not everything. So like this simple formula, of course, you need to understand to memorize it. So in the future, when we check a motor performance, if it doesn't agree with this formula, there must be something wrong. So that is the maximum possible use. So finally, to conclude what we have learned for this chapter, then you can see that now we have been using the equivalent circuitry, trying to understand more about the motor. So that's a really standard equivalent circuitry. You're able to study the power flow for the motor and also the losses. You can also use the formula to understand more about the efficiency than what we learned before, 1 minus S and S. Then we have an air gap dynamic here, which is mainly a correlation between the stator and rotor together. We understand how the efficiency conversion to flow through them. We also discuss about rotating magnetic flux, which appear in the air gap field. So air gap field will interact with the rotor current to create us with the dynamic forces. Then we do have other parameters we have learned here, including the magnetizing, which relate to the MMF there. We also have the magnetic coupling from the magnetizing inductance. This only appear in the equivalent circuitry when we divide them. Yeah. And then, of course, this magnetizing inductance, we cannot measure it, we cannot touch it. It only appear in the equivalent circuitry. At the core loss resistance, we cannot touch it, we cannot measure it, we cannot measure the core loss resistance, but it just appear in the equivalent circuitry. So that's why I can see that the equivalent circuitry only a kind of analytical model, help us to understand the parameter there and help us to have another formulation to understand how to analyze between the rotor and the stator and also the core losses. And then we also using a polarization method, which can convert the low resistance into this format. So you can see that the rotor resistance are with this kind of the equivalent representation, which is able to help us to understand how the slip can modify the output resistance. So, and we also learned briefly about the torque and slip characteristic, the famous curve we learned just now. And then we also understand the different region of operation, including the low slip region near the zero crossing. That's the region of operation. That's also stable region. We also understand the breakdown region is the maximum possible torque. Beyond this one, the torque could break down. So that's why we call it breakdown. And then on the left-hand side of the breakdown torque, there's unstable region with 10 lots to operate them. And so some motor will fall in this region. So later on, next chapter will show you some kind of the control method. You're able to avoid operating in this region too. So you can see that the circuit we show to you are so-called the theoretical equivalent circuitry. You're not able to represent everything, but it's something that scientifically we use this kind of circuitry to help you to understand further, to develop some formulation, help us with the design. So that's how we use it. So finally, there's a number of equations I collected from this chapter. So you can use it as to refresh your mind to see what they are. Yeah.
We touch on the power factor because that's not the power factor correction, right? That's just like your power compared to your KVA, right?
Yeah, you haven't learned the power factor here yet, right? So that's why it's difficult to show everything. And how? So the apparent power. So this item for the apparent power. In theory, our circuitry, you should learn the electrical circuit before the electrical machine, but you only have 2 more years.
So that's why we cannot condense everything together. So that's why in my teaching here, I did not really ask you to understand too much about the power factor. Even though you don't understand the power factor, you still able to understand my inertial moment. But just barely to show to you about, so cosine theta 1 is the power factor. Power factor, basically the simple definition of power factor. Then the current. Between them, there's a phase angle. So this phase angle will be from appearance to here will be how much current lagging the voltage. We don't like that to happen because that will raising some kind of the conduction losses. Why is that? Because PE is the real power, the so-called real power, actual work done or so that's a real power. Real power is the power actually doing the work done, like the motor doing the mechanical rotation. It's really work done. So that means the V times I is the apparent power. You only happen the voltage and current put together become appear to be some power. But that power doesn't mean all of them will be used up to convert into electrical, convert into mechanical output or real work done. So that's how we relate that. And then between them, that will be the cosine phi here. Then you can see that the real work done is the P1. If the real work done P1 is unchanged, here the power factor will be getting smaller. Voltage is unchanged, 120 volt anyway for our motor. So what happened is, if the power factor is in full motor, the same power level, but one motor have a lower power factor, then what's that mean?
The current is in line with the voltage. Or
Yeah, the voltage and current, the voltage will be all the same, say 120 volts for our power line. We plug in two motors in a power point there. Set the same voltage apply to both this. One motor low power factor, say 0.5. The other one will be 0.9. How do you think about how do you comment between the two motors in terms of the power factor? The same power. Same power, that means the two motors deliver the same mechanical power output. So that's what we want. However, one motor at low power factor, another motor at high power factor, then the consequence will be getting one. Yeah, of course, that will be get one power factor. Low power factor will get one. Key thing will be because the
V I cosine, so here equal to fixed. So this also fixed. So if this one get lower, current will be higher. So that means for low power factor motor, the current will be higher, which we don't like because the same motor is same performance, same kind of output work done, but one motor will be high current. That means we need to use bigger cable. We have to use prepare for more power losses, it dissipation. And then you can see that when you do the measurements, check from oscilloscope, you can see that voltage and current have a wider displacement because of the power factor. So that is the consequence. So not only this, because we do have a lot of things discussed about the cosine phi and also power factor. Basically, you can see that. So that means we like a motor have a higher power factor, so you can able to reduce the current. The same performance motor rely high power factor to reduce the current. So inductor, capacitor, they do have power factor issue. So we need to think about how to manipulate with them. Yes.
I was gonna ask, why don't we use a capacitor that aligns the current?
Not only this, it is quite complicated. Some simple and industrial motor method, we can use a capacitor to compensate for the power factor in order to reduce the phase angle here. So we can do that, but that related to the power distribution method. So it's more than that. When you study my course, not my course may not immediately the power distribution, power system, you're going to learn how to do compensation. Sometimes we can add capacitor very close to the motor to compensate. The power factor actually changes. When you change the load, the power factor will be changed. So power factor is not fixed parameter, it's not simple inductor. If you simple inductor in a circuitry, you can use a capacitor to compensate, but motor is dynamic. So you need to use dynamic capacitor, but it's more complicated. Then in this case, you have to use power electronic to compensate for the power factor. When you study my course power electronic in next year, then we'll show you the power factor correction, how to use electronically to compensate the power factor. But you need to wait for 10 months.
Okay. Yeah, okay, but that's a really good question. So basically, power factor is important. Poor power factor will increase the current, increase the losses, which increase all the cable and expenses. Like what you learn in the solar district class. When we see a poor power factor, the current higher, the cable loss will be so high, which we don't quite like. We like to have a minimum cable losses. Because when you connect cable to a motor, the cable could be 10 meters. Because a motor, say, distribution plant, ventilation, fan, fans coil there, that can be 30 meters or 40 meters from the power transformer. So this long cable will cause you a lot of power loss. If your cable with the power factor is low. A motor can have 0.9 power factor or can have 0.6 power factor, depending on how you decide it. So make big difference. Anyway, so finally, you have some reading list. I highly recommend you to check on some of the list to understand more about the background information about industrial motor, three-phase motor, equivalent circuitry, yeah, and also breakdown value. Okay. Any question? Good.